So Sean Hefty you started at the same time as Woody on Open Fabrics, right?
I did.
Yes. And you've been a maintainer all these years?
I have been with InfiniBand before it was InfiniBand.
Okay, so they're in a select company, right? So Sean is an incredibly valuable member of the community, a maintainer, and he's got a really interesting subject to talk about.
So discuss the InfiniBand Scalable SA project. This is a project that several of us are working on within Open Fabrics with Intel, National Labs, Mellanox. So you can see a group of names up here. We've been working on this for several weeks now, a few months, probably 3-4 months. Talk about what we're trying to do with it, what the Scalable SA project is, and what we're hoping we can get to with this project. So the problem, apparently I can't see my animation on my screen here. Yeah. The basic problem is that the SA has an n-squared load on it. So we have a single SM managing the subnet. The SA needs to be able to respond to the nodes. And we have an unscalable situation when you have a lot of nodes. So in terms of the problem, when we're establishing connections, we have to query the SA. So in a general forum, every time we want to connect from one node to another, we have an SA query that goes out, trying to get path information. So use at least one. Communication between all the nodes, obviously that leads to our n-squared problem. So if we have 1,000, 10,000, 20,000 nodes, the number of connections or number of queries we have to place on the SA becomes huge. Other issues that affect scalability in terms of the n-squared, first, name to address resolution. So typically today you can solve this using just host files. But if you didn't have the host file and you were trying to reuse IP over IP, you'd end up using some sort of DNS server to do this resolution. And also IP address translation. So if you're doing IP address translation, typically it's going to be through IP over IP. That's going to end up using ARP. So you have a single multicast group. With that single multicast group, you'll have all nodes talking to all the other nodes, trying to find out what IP address maps to what InfiniBand address that they can use. So presented on some of this before, but with the ARP case, for example, there's ways to kind of help fix that problem. You have to increase the ARP timeout. But because when you go to 10,000 or 20,000 or a lot of nodes, basically your ARP timeouts need to be on the order of days, if not weeks, for it to have any effect. Otherwise, you end up having hundreds, literally hundreds of timeouts in the ARP caches every minute. So I've introduced before at this conference, and I have the code available, a concept called IBACM. That's the assistant to the communication manager. This is a daemon that runs that was intended to try to help solve these problems. So if you've heard me talk about IBACM before, you can ask yourself, well, doesn't that solve this issue? And we'll look at what IBACM does versus what this is trying to solve. So main issues. First, processing is still centralized. So we have a single SM. The SM is responsible for doing all the processing. It needs to construct these paths. So when a node wants to connect, he sends a message saying, hey, I need a path between IP address point 10 to point 11. The SA needs to convert that information based on the raw data, that's the switching tables, create a path record, and return that to the user. So this is still a centralized processing that's done. We can form caches. So the IBACM, for example, has cache data. The issue with that is we need to keep these caches somewhat current. So if the cache gets out of date, how do we continue to refresh that cache? So other proposals, including some that I submitted, will collect a bunch of data from the SA, cache it locally, but then it needs to update the cache at some point. So at some point you need to time out the cache, go up to the SA, and collect a whole new set of data. Well, that ends up being a scaling issue when you have, again, 10, 20,000 nodes all going to the SA saying, hey, give me a full listing of all the path records again, because my data may not be up to date. And then you have timing window where between the cache expired and the data is no longer valid until you actually go out and get it and bring the new data down. Today, MPI uses static files, which works well if you have a homogeneous cluster or if you have very specific routing topologies. But if you have a heterogeneous cluster with link speeds that are different or certain routing topologies like torus routing, then this mechanism of using static files doesn't end up working. And then finally, we have heavy burden placed on the single multicast group. So this is IP over IB. So IP over IB creates a multicast group throughout the entire subnet. And when it does address translation from an IP address down to an InfiniBand address, all that traffic ends up hitting this single multicast group. So our solution, so truly novel solution that's supposed to be my sarcasm font, is we're going to look at, can we actually fix the problem of the SA scaling? So far, the solutions have been trying to not change the SA and simply have a solution that works around what the SA and what the SM are implemented to. So we're looking at trying to extend the actual implementation of the SA in this case. And by extending the implementation of the SA, it gives us the ability to have increased opportunities for solutions. Right? We're no longer restricted to just being able to send a MAD, 256-byte packet, for example, to get this data. Now we can use connected communication. So other ways of communicating to distribute the data that we need and get it down to the clients. This is an open source effort. We have Git trees on GitHub that have all this data, or all the work that we've done so far available in it. And it will be open source. We're focused on having both scalability and reliability. We assume that when we have tens of thousands of nodes, the chance of a node being down is extremely high. So we want to build into the scalable SA not just being able to distribute the data, but also handle the cases where we have faults. We'll talk a little bit about how we're going to try to do that. And I want to mention that we are dependent upon the SM. So we are not introducing a scalable SM. We're assuming that the current SM is going to be what's used to actually configure the subnet, manage the switches, program the lids into the end nodes. This is dealing only with the SA part at this point. So we've had discussions about can we take some of these concepts and bring it into the SM, but at this point our focus is really only on the SA portion. So this is really what the end nodes need to have. In InfiniBand terms, we're focused on basically the Q pair 1 traffic, not the Q pair 0. So what are the goals that we're looking at? In terms of the size of the subnet, we're looking at basically 40,000 nodes. And I'll show you, we'll have some analysis of what that looks like when we try to scale up to 40,000 nodes. But that's about the range we're looking at with this. We like to go as large as we can. InfiniBand addressing, there's no strong need, at least with current IB addressing, to go beyond 40,000. I mentioned before about topologies. Basically, any topology we want to be able to support. We don't want to put a restriction on that if we can avoid it. Heterogeneous clusters. We don't require the links to be the same speed. I think this will be true as much larger clusters now are probably mostly heterogeneous at this point as new hardware comes available. And we also want to have minimized impact on the compute nodes. So we don't want to have updates, a lot of updates going to a compute node while it's in the process of running a job. And we also want to limit the impact on the subnet itself so we don't impact a job that's running. For example, if we're trying to update caches, we don't want those cache updates to go ahead and end up impacting a job and slowing it down. So the way we're trying to do this, we want to have distributed processing. So our scalable SA, we're assuming that we can have this work done across multiple nodes. So we want multi-threaded and multi-processed and different nodes. We want to ensure that we have consistent data throughout the caches. So this is one of the issues is how do we have 40,000 nodes and they all have localized data. How do we ensure that that cache is consistent? We want to avoid any large single multicast domains, so we're not building this on top of IP over IB, for example. We're hoping IP over IB could plug into this, but this is one of the reasons we want to be able to use like native InfiniBand addressing, native InfiniBand schemes in order to support the scalable SA work. And our last main goal is we want this to work with existing applications that are written to the RDMA CM. So if the application is already written to that interface, they wouldn't need to change to make use of this. So we did some analysis based on those goals and what our general objectives were. Starting with, we looked at 40,000 nodes. What does that end up looking like at the SM level? Well, 40,000 nodes is 1.6 billion path records. So that's the number of path records that you're dealing with across the entire subnet. In terms of the database size, what we looked at is that shows up as about 500 megabytes worth of raw data at the SM level. So that's the amount of data that we're looking at. Say, well, can we just replicate the SM database? So at 500 megabytes, no, we don't want to replicate 500 megabytes worth of data to 40,000 nodes and then try to keep that consistent. It's too much data. At the SA level, we looked at was, for the SA to do the calculations, at 1.6 billion path records, it's going to take it about 1.5 hours to do those calculations. So that's a lot of time just to do those calculations. Now, even if we can reduce that by a factor of 10, you're still looking like 10 minutes of the SA just plugging away trying to do the calculations. So this is where we're getting into, we want to be able to distribute this work because we can't have a single system do this sort of large-scale processing for an hour and a half while your end nodes wait for their path records. We looked at how many queries the SA could do. We measured it can do about 50,000 queries per second. So if it was responding with data, 1.6 billion path records one at a time, it would take it about 9 hours to actually distribute 1.6 billion path records. So again, obviously we can't do that. We need to get the data, the processing distributed, and the data distributed so that we don't have this single bottleneck. Now, the one good news we had is on the compute nodes only need each 40,000 path records on average. So in the worst case, you're looking at about 2.5 megabytes worth of data. So 2.5 megabytes worth of data cached at each compute node, that at least seems doable. So the model we selected, and broke it up into little areas here. For the computation, obviously we want it distributed. We want the administrators to be able to select which nodes. So we're going to introduce the concept of having management nodes. You'll dedicate a specific number of nodes for management purposes only. So we're not impacting the computations of the compute nodes or NPI running. We want it to be multi-threaded, so we still need to be able to scale within a single system. We're going to introduce the concept in the architecture we're using should provide lockless access to this data, including lockless updates, so we can pull updates, update the cache data on each of these management nodes without serializing all access. The data itself, we expect it to be calling it weakly coherent. So when we have 40,000 nodes, even if we only had a couple hundred management nodes, there's just no way we can keep the data on all those nodes completely consistent all the time. So we recognize that we're going to have cases where the data in certain nodes are going to be different, and the protocol's intended to be able to support that. Eventually, now we're trying to get it to where all the data will be the same on all the nodes, but while updates are occurring, we'll have this inconsistency. We use incremental updates, so we're not pushing down this 500 megabyte database all the time. Basically, we copy the database down to the nodes, and then we just want to be able to send small updates. And for the communication, so the incremental updates, that's so we don't have to have a huge impact on the subnet. We also need to be able to detect and report all errors. So again, we want scalability and reliability. So reliability, we want to be able to detect these errors and report them up and be able to deal with them and have some sort of failover. So what does the internal architecture look like? So at a high level, this is our general architecture. Kind of have 3 layers. I called it core distribution access layer. I stole Cisco's terminology. So our top layer handles the management of this distribution. Our distribution layer handles actually pushing the data up and down the tree. At the bottom, we have an access layer. This is responsible for doing, for example, the path record computations. And then we have our compute nodes or the clients down at the end that have some sort of localized caching. So in a little more detail, our core layer. So what does the core layer look like? Well, first, we have to be able to find the service. So we assume that the service can be found at the SM lid. So everybody will connect to the SM lid. The purpose of the core layer is to extract the raw data. So it's going to communicate with the raw SM database, extract it into a format we can use to push down this tree. Nodes throughout this tree will end up sending messages to join. So they'll try to join into this distribution tree to extract the data. The core layer is responsible for forming that tree. So it just manages basically who gets placed where in the tree and then rebalancing the tree. The distribution layer. So this layer is designed to be data agnostic. So it's not aware of what data it's pushing down the tree. It just says, okay, here are a collection of database tables. Here's a log file. Push this data down the tree and apply the transactions. And we're doing this specifically so we can allow additional data to be pushed down, up and down the tree later, so we can extend the model. So our database model is based somewhat loosely on a relational data model. We're not implementing a full database here. We're not doing an SQL language. We're just pushing up and down data tables and basically transactioning. We do have the concept of data versioning. So call it an epoch value. So we know at any point when we look at any point in the tree, we know what version of the data they're dealing with. And this is why we can keep it consistent when we have nodes move from one node to another throughout the tree. And then the transaction log is used to help us with the incremental updates as long as providing the lockless access to the database. The access layer, I mentioned this is data aware, so this layer has to be responsible for taking the raw data and converting it into, like for example, actual path records. It'll handle select SA queries. So the interface to this will be, I can do a path record query, but it'll also support some higher level queries. A higher level query being something such as, here are 2 IP addresses, give me back the path record. So I don't have a multi-step process. And it also does make use of the epoch values to notify the client nodes when there's been changes to any of the data. So it'll update an epoch value, which basically is just like a 32-bit or 64-bit integer. It just increments a counter. And that way the clients know that there has been a change, but the client doesn't have to do anything about that change until it reaches a point where it's convenient to do so. That way we minimize the impact to those compute nodes. We don't start pushing down a large number of database changes. For the clients, this will be integrated with the IBACM, so we're not tossing IBACM. IBACM becomes the client node that actually interfaces to this. Users of the libRDMACM already have access to the IBACM daemon, so that doesn't change. Long term, we want this to be able to collect stuff like the host name and IP addresses and actually push this information up into the SSA distribution tree. So the SSA tree can collect that data and then push it back down so we can support these higher level queries. And we're not relying on stuff such as ARP to do this sort of translation. And it has our localized cache that we're maintaining at each client side. This is at 2.5 megabyte worth of data or so that we're storing at each end node. In terms of reliability, we define both primary and backup parents. Originally, we were going to call on mom and dad parents. We couldn't figure out which one was the primary. So we would connect these up. You can have pre-established connections so we can quickly fail over. So that, again, this uses a connected model. This is not exchanging data through datagrams. This actually uses connections that's built on top of, the plan is anyway, to build this on top of our sockets. Oops, I'm going the wrong way. For error reporting, so if a node goes down or loses connection, it'll automatically switch to the backup parent. For reporting, we have the parent of whatever node has failed. That is responsible for actually reporting the problem up to the core layer so the core layer can take some sort of action. The reason we chose the parent doing reporting is we didn't want a node to go down and have all the children of that node switch to a backup and have, say, 1,000 children all jump in and say, hey, my parent's gone. So we want just basically the grandparent to be the one saying that there's an issue that's occurred, and I don't know what it is, but somebody at the core layer needs to come take a look. And again, the database is defined such that when we have a failure, we don't know when the failure is going to occur. We assume the worst case. So we could be in the middle of an update. The tree could have updates on, say, the left side, but not the right side. And we need to be able to detect when we do a failover from a primary to a backup parent, it may be a case where we actually have the child now have a newer version of the data than the parent. So we use the log file in the database architecture to kind of try to recover from this sort of issue and ensure that we stay in sync. Question? No. So summary, we're kind of scalable, distributed SA. So it will work with existing applications. It's fault tolerant. So what's the catch? Well, the main catch is that when you look at our development phases, we are roughly at 0.01 alpha release. So there's obviously quite a bit more work to do. So our goal, the short-term goal, is to have a release that does basically just path record distribution. So we designed the architecture to be extensible. We want to be able to collect, for example, events up the tree, address information up the tree, but we're nowhere close to that at this point. In terms of deployment, I'm picking a target 2013 release date. So hopefully we can have something that's some sort of preview release available by the end of this year. We'll see how reasonable that is as we get closer to the end of this year, but at least that's. So my personal goal, I told the people right before this presentation, the other members of the team, that I put this date on here. So if they don't like this date, this is all my fault. So what we're expecting this to have is when we have the SSA finally released, we're expecting a package that's a core package that would be, for example, installed on the SM node. We expect on very large subnets that you would have some number of management nodes dedicated for this purpose that would have a different package, our distribution package for the SSA. So there's going to be a lot of functionality. So, for example, the core package may actually have this core distribution and access layers. We have these layers in the architecture, but each of these are the packages that you would actually end up installing as an end user. And then the compute nodes, you just have IBACM. Which ship with the distros, but obviously we need a newer version of that. And again, we'd also like to get the IBSSA packages in with the distros as well, so that these just come with the distros and just work. And that is it. Questions?
Okay. Thank you, Sean. That's great. So do we have any questions?
Yes. Yes, we want to control how much jitter is actually hitting the compute nodes, especially when it's running jobs. So that was one of the requirements that the labs were requesting.
Could you go back to the graph you showed us a second ago?
Maybe. Which graph?
So without having thought this through at all, are there issues related to the fact that different layers in the graph are going to see the results at different points in time? We already talked about semi-coherent, I know that.
Mm-hmm.
Is that likely to be an issue?
We don't expect it to be an issue. So our biggest concern is, so incremental updates, we don't think that'll be an issue at all. It's when we have wide changes that require a full update of the database. And that's some of the discussions that we've had, is when we have to push down a full update of the database, how do we do a full update, and does it actually affect the end nodes? And our belief is even when we get out of sync on this data, it's the raw data that's getting out of sync. When you get to this access layer and the path record it computes, in most cases the path record is going to be exactly the same. So we don't know that we're going to end up with changes at the client, at that client level. His path records may never change, even though we have changes within the fabric and changes within the switches and the links. Most of the paths, most of those 1.6 billion paths anyways aren't going to change.
So again, I haven't thought about this anywhere near enough to know if this is even partly sensible, but if different layers in that chart have different information at different points in time, could you wind up in a situation where you inadvertently create a deadlock in the fabric?
So these aren't doing the programming. This isn't the SM, right?
I know. If someone is reading that database and using it to program pieces of the fabric.
No, the answer is no. You can't create a deadlock.
Great, good answer, thank you. Why not?
Yeah, that's why you want to answer. Yeah, he's a better person to answer this than me.
Who has the question?
So if I understand your question correctly, you're asking if you use SLs to avoid the credit deadlocks within your fabric, and somehow the routing changed in a way that you will inject traffic on the wrong SL, going from point 1 to point 2, will this create deadlock? So the answer is that if you will have a deadlock, it will not be infinite. It will eventually be replaced by correct information, and head-of-line blocking will remove the deadlock by itself, and the situation will recover. So the consistency of the data in cases where you use SLs may cause a momentary wrong SL being sent. Doesn't have to deadlock, and the credit loop may be there, but it doesn't have to deadlock. And if it deadlocks, then it recovers after some time.
So it wouldn't persist.
Yes.
And also tourist routing. I'm trying to think at the end node, the SL is fixed, so that wouldn't happen there. I mean, it might be a problem for Lash, which isn't used in general anymore. And I'm trying to think. I don't know about the new DFSSSP. I think the SL can change there.
Any other suggestions, inputs? Okay.
Sort of follow on. You definitely have to think about different topologies and future topologies as you're doing this. And the number 40,000 seems a little shy.
Well, so with InfiniBand anyways, we only have 40,000 lids, right? 42,000 lids. So
Change it.
But you probably assume that's going to change.
Yeah.
well, we're hoping that this just scales, right? That there's nothing in that we believe that's going to cause us to break at 40,000 or 100,000 versus the SM. I think the SM will break first.
Okay.
Well, it's, yeah, going to be our problem again, but.
So you have this distribution network here, and sometimes there are changes that get pushed down. But what if I guess what have you done to sort of make the distribution network itself sort of resilient? I mean, maybe the links that fail are the ones that go between, one layer to the other layer or something like that. I mean, or the addresses change and so forth. So
It's like this is showing. So if we lose a link for the management nodes, between the management nodes, right? So again, it assumes that whoever's the administrator, that it's wherever he's placed those management nodes in the tree. So we can't really control that. But the management nodes can fail over to other management nodes. So we'll support that.
So is it the case then that at any one moment they'll know where to go to get the, if whatever link that they used before doesn't work, or the address that they had before to get their updates, doesn't work,
So
then they'll know.
In practice,
all the
what
way
we would
back up to the
expect,
SM lid
so
or
yeah, in
whatever?
practice we would expect them to have both a primary and backup already pre-assigned. There's nothing that prevents them from connecting to both the primary and backup ahead of time. So they don't have to wait for the failure of the primary before switching to the backup. They can already have a connection to the backup available and immediately switch over.
Okay, is it the case then that, so because you have that kind of capability, are you thinking that you could actually dynamically adjust your distribution network too, as, I don't know,
Yes.
load increases or whatever,
yes.
or decrease it after?
We're
yeah.
assuming that we'll have load balancing because we don't know how many nodes are going to join up front.
Right,
So we
right.
build the tree. Well, basically, we'll do some sort of join. There'll be a delay built in until the SMs discover the fabric, so we know what the trees are going to end up looking like. and then we'll start forming the tree. But if you connected two subnets together, then we'd have to deal with the case of just rebalancing, for example.
So maybe you have an access node that says, hey, I'm getting a lot of traffic. Can you like widen the tree a little bit here or something?
Yeah, so,
okay.
so we've talked about, for example, monitoring, and the core layer doing monitoring and coming down and figuring out, okay, how many clients are coming to this access node, how many errors are they getting, for example, those sort of things. So we want to have the monitoring kind of built into this framework.
All right. And are you going to deal with, traps, notices, stuff like that too?
Eventually, yes, that's part of the plan.
Any more questions? Okay, Sean, thank you very much.